We'll go from current slide. I apologize again for my voice. Actually, the voice is a little better than it was last week, but the cough has gotten worse, and that basically only started recently. Actually, my throat started hurting again pretty badly this morning in my first class, and it's gone downhill from there, but I think I'm better off than I was last week. Anyway, so much for that. The only major announcement I know about is the fact that we do have our SECS team here. Those are the Southern Association of Colleges and Schools. They are our accrediting agency, and they're here for the site visit. This happens once every 10 years. You hope not more frequently than that. And we've been working at it for well over a year now, doing all the paperwork and the planning and everything else for it. And my throat hurts. They're here now. They just come to check and make sure you are doing what you said you were doing, and in the ways you said you were doing it, and you corrected things in the way you said you were going to correct them. Because in the written part, they did send back comments and things for us to correct and get or change or whatever. And as long as we've done that and everything is as we said we were doing, it should be a pretty smooth visit. Now, what I heard that surprised me was they were basically mostly on this campus today, and they'll be on Birmingham tomorrow. So if you still see them running around today, Dr. Anthony and Mr. Hobbs are with them this morning, is what I understood. Don't know where they are now. They may have gone over to Birmingham. They may still be here. Don't know. But anyway, they will probably still be on one of the campuses, probably Birmingham, mostly tomorrow. And then, if everything's in good shape, they may be leaving by tomorrow afternoon, which would be a very good sign for us, meaning they are through. You know, if they're still hanging around, that may not be such a good sign for us, meaning they found some discrepancies and they're wanting to talk about them, that kind of stuff. Now, that's all speculation on my part. They may be planning to be here 3 days no matter what. So, but that's how I'm guessing it may be going to pan out. So anyway, if you do see them, be kind to them, you know, treat them nicely. They're visitors. And we will, hopefully things will come out really nicely. Okay, then specific to this course, we are in Chapter 4, and we'll continue in Chapter 4, and I'm guessing we're probably going to finish Chapter 4. At least we'll get a good way toward finishing Chapter 4. And if we finish Chapter 4, we're going to get started on Chapter 5. If we don't, we still have some time on Thursday. We can still work on 4. I'm sorry, we don't do Chapter 5. We move on to Chapter 6. Okay? So, no test today, but hopefully we will get far enough to get a lab today. I think that's almost a given. I can't set it up until right at lab time because I need hot water, I need ice, I need other things, and if I had them set up now, they would be ambient by the time we started. So we'll do about 2.5 hours of class, hopefully finish Chapter 4. If not, we'll end at 2.5 hours. If we do finish 4, we're going to start on Chapter 6. Okay? Then we'll have 2 hours of lab. I don't think it'll take you 2 hours, but I will allow at least 2 hours because that's what we're set up for. All right, any questions on anything so far? Let me just say this. I have finally received the first paper in, all right? And good to know, good to have, like to have some more because we've still got 12 people haven't turned it. Oh, look at this.
That's this class and this is the math class.
All right, good deal. One more for this class and one for a math class. Good deal. That way. Okay. Lab 1s, I think I've returned those to you. Test 1, still one person out who has not completed test 1. Lab 2, 1. 2 people haven't completed lab 2. Lab 3, 1 person hasn't completed lab 3, or turned it in anyway. Lab 4, I think I've returned those, is that right? Have you gotten lab 4 back yet? No. Let me go on and get them to you so I don't have to carry them around anymore. Okay. Okay. I've returned lab 1. Can't do 2, 3. Lab 4. Oh yes, I have returned them. It's the forces and momentum lab. It's just 2 people aren't here and weren't here when I returned them. So hopefully the rest of you have those. That's lab 4. Test 2, still missing 1, 2 people for test 2. Lab 5, 1, 2 people for lab 5. Lab 6, 1 person for lab 6. Test 3, 1, 2, 3 people haven't done test 3. And lab 7 was the lab we did last time. We've only got 1 person missing that one. Okay. So we'll be doing lab 8 today, if we can ever get started and move along.
Did you scratch me off for the last test?
Say again?
Did you scratch me off for having taken the last test?
I mean, I've got your grade in the grade book, if that's what you mean.
No, when you said so many people had not taken it, I didn't.
Well, no, I've got your grade in the grade book.
Okay.
So that's people who don't have grades in the grade book.
Okay.
Okay. So, please, folks, get caught up. And I keep having people say, I'll see you Tuesday. I'll see you Thursday. I don't see them. Okay, so please try to get caught up when and if, as soon as you can. All right, any questions before we move on?
What page are we on?
We're on page 96. This is chapter 4, heat and temperature. The section that we're on now is the heat section. We actually did temperature, then heat. And we're on page 96, almost the top of the first column, measures of heat. Same title as this. All right. Now, we have little bits of, I guess, history issues here. Originally, heat and energy were considered to be one of the elements. Remember Aristotle's 4 elements: earth, wind, water, and fire. Fire being heat and energy. Well, that was considered to be an element. Definitely not an element. Okay? But even after that was debunked and they realized there were many, many more elements, they still had the list. Lavoisier compiled the most comprehensive list up to that time of something around 37 elements. Few of those were not elements. One of them was one they called caloric. Again, heat, fire, energy, not an element. Okay, so that's where the name calorie came from. Early on, they were measuring heat by this term called, well, this was after they were considering it an element. When they finally considered that it was indeed something else, they gave it this unit, calorie, named after what they thought was the element caloric, or somehow they had it mixed in there. Now, this is somewhat of a metric unit. Okay, it's not SI. SI is down here. This is a metric unit. No, not quite here. Sorry, SI is not. There's the SI unit. joules. Because even after they decided it wasn't an element, they still didn't know that it was just another form of energy. So therefore it had its own units of measure. Whereas in reality, it was just another measure of energy. And this measure was, sorry, the calorie. And that was defined to be the energy needed, at that time they called it the amount of heat needed, to raise the temperature of 1 gram of water, the most abundant compound on the surface of the earth, water. 1 gram of water, 1 degree Celsius. Now that was it's not quite SI, but it was considered to be, gram certainly was a metric unit. Celsius was sort of considered to be a metric unit. So they considered calorie, which was the amount of heat needed to raise the temperature of 1 gram of water 1 degree Celsius. Now, a gram of water is 1 cubic centimeter of water. Well, if that's the centimeter, that's the centimeter, and that's the centimeter, a cube of water, 1 cubic centimeter of water, was very little, okay? Have you ever given medicine in the medicine dropper to, say, a kid or an animal or something? 1 milliliter of water. That's just a few drops, okay? That was what the amount of heat needed to raise that 1 gram of water 1 degree Celsius. Now 1 degree Celsius is an okay temperature, but not a huge amount of temperature. So this is a very, very small unit of heat. Now we're calling energy, which it is. So they went up to the thousands of those. Kilocalorie, okay? Now, that's KCAL. Now, because this one was so small, oh boy, y'all are all healthy today. Nobody has a food element. Oh, there's one. Does that have any calories listed on it?
None.
All right. What does it say, really? You don't have to say the number, but it does have calories listed, right?
Yeah, it's 150 per serving and 400 per package.
Okay. Now, I bet you that's not little c calorie, that's capital C calorie.
Right.
Yes, okay. Here's the difference. The nutritionists, the people who measured how much heat content as you metabolize your food and how much energy you can get out of it, that was what the measure of calories are. Meant to be the same as this. But they were dealing with such huge numbers, and they didn't want to call them kilocalories. That was too many syllables to say. So they just started saying, instead of kilocalories, they called them calories. But they made it a capital C calorie. So that's why when you see how much energy, heat, or whatever is contained in a material, if it's a capital C, if it's anything to do with food, that's usually a capital C calorie, which is actually 1,000 of these little calories. It's energy net needed to raise 1 kilogram of water 1 degree Celsius. Now, most of the bottles I see here are probably a little less, well, maybe not, Thomas. Is that a liter or what is that? No fluid ounces, really?
Yeah, it doesn't say how much it is.
20 fluid ounces.
20 fluid ounces.
Oh, yeah, liter.
That's a liter.
Sorry.
So if he had that filled with water, which at one time he did, I bet, then that would be 1 kilogram of water, because 1 liter of water, pure water, is 1 kilogram. The amount of heat to raise a full kilogram of water, 1 degree Celsius, that would be a kilocalorie. That's a pretty hefty amount of heat or energy, okay? So that's how the metric unit came up with that measure of heat. Again, they were dealing with heat, now we're calling it energy, but at that time it was heat. Over in the English system, again, they were thinking this was different from energy. So in the English system, we had foot-pounds of work or energy, but they thought heat was something completely different. And the British came up with a British thermal unit, or BTUs. And I bet you Mark has dealt a lot with BTUs, right? That's how they measure AC units, or they used to. I don't know if they still do. Yeah, so BTUs, that's British thermal units. That would be the unit needed to raise the temperature of 1 pound of water. Okay, now a pound of water is not quite as much as a kilogram of water, okay? But it's 1 pound of water, 1 degree Fahrenheit. Now 1 degree Fahrenheit is, as you know from the last lab, about 1.8 Fahrenheit degrees makes 1 Celsius degree. So this is a smaller amount of increase, but you have a smaller amount of water. So basically, a BTU and a kilocalorie are more similar. They're not the same. Kilocalorie is a little bit more than a BTU. Now, once they finally realized that energy and heat were really measuring the same thing, they determined that 1 calorie, little c calorie of heat, was the same as 4.184 joules of energy. And you thought a calorie was small. A joule is even smaller, less than a quarter of what a calorie is. So in reality, we're probably most of the time dealing in kilojoules, maybe even megajoules, because a joule is a very, very small amount of energy. All right. Now, a couple of things they left off of here, and let's see if I can find them for you here. Of course, these next couple are really easy to do. I thought somewhere they had some more equivalences here, but I don't see them now. Must have been a previous thing, but let's deal with just a couple of these. I think I'll go to the yellow type because this is dark background. This means 4.184 kilojoules would be 1 kilocalorie, which is also 1 capital C calorie. Okay? And the one they list in the book is, and it's okay too, but 4,184 joules is 1 kilocalorie or 1 capital C calorie. Okay. The reason they call the mechanical equivalent, this would be mechanical energy, this is heat energy. Okay? So those are the equivalences there. I know somewhere here they make the combination of the comparison of joules, of BTUs to calories, but I just don't see it. So let's see if we can find it somewhere else, like in the front of the book. Energy. Okay, we've got that 1 calorie is 4.184 joules, and you got that 1 joule is 0.738 foot-pounds. We did that one before. Here we go. 1 BTU is 252 calories. So 1 BTU is 252, I think I said. Oh, I've lost it now. There it is. 252 calories. That's little c calories, which would be 778 foot-pounds. That doesn't quite seem right. No, yeah, that's okay. That's right. Okay. So foot-pounds is a fairly small amount of energy as well, because that still doesn't seem right. I think they've got a decimal off there. No, I guess it is right. So foot-pounds is a really small amount of energy. Okay. Okay, I guess that's all you need. So basically, I think of this way: a BTU, British thermal unit, is approximately a quarter of a kilocalorie, or a capital C calorie, because it would be 0.252 capital C calories, which would be 0.252 kilocalories. Okay, so BTU is a pretty hefty amount of energy. Not as much as a kilocalorie, but it's about a quarter of a kilocalorie. But it's many times more than a little c calorie. Okay. All right. That said, let's see if we can find, here we go. Let's do example 4.4, page 96. A 1,000 kilogram car. And for some reason they make 5 significant digits here, which I'm not at all sure they ever have. Kilogram car. What is that a measure of? What are you measuring kilograms? Mass. That's the mass of the car. Okay? Is moving at 90 kilometers per hour. 90.0 kilometers per hour. Which they tell you is the same as 25.0 meters per second. We could have figured that out on their own, but we thank them for giving it to us. What's that a measure of? That's the velocity of the car. Okay? How many kilocalories are generated when the car brakes to a stop? So we're looking for how many kilocalories are generated when the car brakes to a stop. Okay? How are we going to do that problem?
Well, we could find the answer in joules.
Okay, and how do we get it into joules? Okay? What is being described here? A car in motion. So guess what kind of energy that is? Kinetic energy. And what's the formula for that kinetic energy? 1/2 mass times velocity squared. So we have, let's just call it 500 kilograms. I'll put a 0.0, though it doesn't make any sense really. Kilograms times 25.0 meters per second squared. Now, if I'm not mistaken, this is 500.0 kilograms, and my memory is this is 625, you can put a 0.0 if you want to, meters squared per second squared. Yay or nay? I think that's what 25 squared is. So multiply those out, and what do you get? Quite a hefty number. 3 PHS112 00. 312,500 what units?
It's joules.
Joules. Kilogram meter square per second square is a joule. Okay? And we wanted to know how many kilocalories are generated when the car brakes to a stop. Now, where is the heat generated when a car brakes to a stop? Anyone know? It could be some. The major place is your brake drum and your brake pads, or however they do them these days. Okay? That's friction. And when you hit the brakes, friction produces a lot of heat. That's how much energy that has to be changed to heat. So, what's the conversion of energy to heat? Again, let's go back to this one. Kilocalories to kilograms. Right. Kilojoules to kilocalories. Okay? What did you say?
It's 1 kilocalorie over 4,184.
Okay, he's making a conversion here. He's putting kilocalories here and joules on the bottom. And he said 1 joule was what? No. 1 kilocalorie on top. Okay.
That's 4,184 joules.
Okay. How about let's just changing this, move in the decimal there and make that a kilojoule, and make this a kilojoule, and that'll be 4.18 what 7? 184. What is it? 84. Okay. And just not even mess with joules. Get it right to kilojoules. Okay. So 312.5 kilojoules divided by 4.184 kilojoules, and what does that give you? Something on those. 74.7 kilocalories of heat is generated by stopping that car that was moving at 90 kilometers per hour, which is pretty close to 60 miles an hour, right? Okay? And you came up with about 75 kilocalories, or 75 capital C calories. Now, do you still have your bag of chips? Mark?
Yes, sir.
How many calories were in that?
It depends. You talking about per serving or per bag?
Well, per serving will do.
150 per serving.
150 per serving. You could have stopped the car twice with that. The energy that was in that was enough to stop the car. A half-ton car, no, a full-ton car, that's actually more than a ton, going 60 miles per hour, you could have stopped 2 of them with that bag, the energy from that bag of chips. What? Yeah. Now, yeah, there's other things going on too, but that's how much or little energy we're dealing with, okay? That's how much heat is generated by that. They got 74.7 kilocalories. Good deal. Any questions on that? Okay. All right, so that's measures of heat. The next topic we hit is specific heat. Okay? Now that's yet another bag of worms, you might say. What specific heat is dealing with is, all right, let's take that bag of chips, okay? If he had a bag of carrots, same mass of carats. That wouldn't be very many carats, by the way, because that's fairly low mass. You think it'd have more or fewer calories? Fewer, for sure. Okay? So you see, different materials may have different amounts of heat. Now here's the an example I participated with once. We had a physics meeting down near Central, I think it was called Central Alabama Community College or something like that. And is that near Sylacauga? Yeah, that's the one. Huh?
Where did you say?
Okay.
What did you say? Where did you
Yeah, near Sylacauga?
Yes, Sylacauga.
That's it. Okay. And we were having a physics meeting down there, and there was a group that brought these things that were really nifty. It was basically a metal plate. I'm guessing about that big, but it may have been a little bit bigger, something around that order. And in the sides of it were drilled, it seems like about 8 holes. And in these holes you could fit pegs. They look like golf tees almost, but not quite shaped that way, but somewhat similar. Fit them snugly into each one of those holes. Okay? The thing is, these 8 different plugs, just to think of a better word to say, were made out of different materials. I remember there was an aluminum one, there was a copper one, there was an iron one, I know there were several others. There were 8 of them, different metals. Now the plate itself, I'm guessing was metal or aluminum or something. That really didn't matter, but it was one uniform plate. And we each plugged our spikes into that, and they turned on a Bunsen burner underneath the middle of the plate. Square in the middle of the plate, well, round in the middle of the plate, right? Dead center. Okay? And we each held our plugs in the holes. And finally, one guy let his go. Okay? Was he the biggest wimp in the group? Not necessarily. After a while, another one let his go, or hers, whose ever, and they kept going around until finally the last one let it go. Now, and it was quite a while later, after the first one did. That first one was just a big wimp, and this was a mighty high tolerance for pain person. No. The difference is that different materials have different specific heats. What do we mean by specific heat? Well, here are some of the variables involved with heating, and this is how we came to specific heat. Of course, if you add heat to a material, heating a material, you're going to change its temperature, for sure, right? The amount of mass, that's one variable. Remember we talked about the thimble full of water versus the half tub full of water? Much more mass here, very little mass there. Yeah, that influences too, okay? Then the last, or the next one, the type of material. Different materials require different amounts of heat to produce the same temperature change. What measures that is specific heat. And it just happens to be, if I'm remembering this rightly, well, we'll see in just a few minutes. It's summarized in one equation. Okay? Here comes the equation. Well, not yet. Okay. Here's an illustration of this. Okay? Oh my goodness. They decided to show today. Yeah. I figured you were here. All right. Good deal. We're talking about specific heat, which is, we're about to get to the definition, just the fact that different materials require different amounts of heat to produce the same temperature change. If you had 10 grams of aluminum, now this looks bigger because aluminum is less dense than copper. But if you had 10 grams of aluminum at 20 degrees Celsius, anyone know about what 20 degrees Celsius is? I think we did it in an example last class. Room temperature. about 68 Fahrenheit. Okay? So, this is right around room temperature, and you heated it up to 100 degrees Celsius. Now, I'm guessing you had it in a pot of boiling water. So when it got up to 100 degrees, that's where the water was boiling. So how much heat was required for that? To get this 10 grams of aluminum at 20 degrees up to 100 degrees. It took 176 calories of heat to be absorbed, and that gave aluminum a specific heat of 0.22 calories per gram degree Celsius. Now, even though we were just talking about how small a unit calorie was and how small a gram was, that's still the most convenient units to deal with because you don't have to exchange a lot of heat. Okay? But again, on the other hand, if you were cooling this 100 degree cube of aluminum down to 20 degree cube of aluminum, again 10 grams, then you have to lose 176 calories. But if you had copper, 10 grams of copper is a much smaller block, but still 10 grams. At 20 degrees Celsius, it only takes 74.4 calories to heat that to 100 degrees Celsius. That gave it a specific heat of 0.093 calories per gram degree Celsius. That's less than half of what aluminum was. Okay? And then to it would be 74 calories this way. But if you had 10 grams of gold, head to the bank, folks. I'm sorry, that's beside the point. You're a rich man, okay, or woman, okay, because that's very valuable. 10 grams of gold is even smaller because gold is more dense than copper, but there's 10 grams. It only takes 24 calories. I guarantee you they didn't have any gold pegs. If they had, they wouldn't have them for long, okay, because someone would have ripped one off. That was the experiment I was talking about before, okay? So that only requires 24 calories to be absorbed to change it to 100 degrees Celsius, or released to change it back to 20 degrees. That gave you a specific heat of 0.03 calories per gram degree Celsius. That's less than a third of what this was. This was less than half of that, less than a third there. So if my memory's right, the guy with or whoever it was with the copper peg, that was the guy that released it first, because it didn't take that much heat to raise its temperature to where it was burning his fingers. Okay? Then the next, it seems like just about the last one was aluminum, and finally it got too hot for that. And there was considerable amount of time change, because this would have been more than twice as long for that to get hot enough to burn your hands. So that's what we mean by specific heat. Okay, here's the equation coming out of ether space. There it comes. Q. Okay? Now in this chapter, capital Q is going to stand for heat. Okay? Pretty standard. In the next chapter, chapter 6, little q will stand for charge. Why they use the same letter, I don't know. But in this chapter, capital Q is heat. M is your mass. C is your specific heat. That depends on the material. And delta T is your change of temperature. So there's your formula. Q is equal to MC delta T. Okay? Now, of course, you could get at least 3 more equations out of that one. We don't use them that much, but you could. M would equal Q over C delta T. We will use that one some. You could get C is equal to Q over M delta T. We will be using that one for sure. And you could get delta T is equal to Q divided by MC. Okay? So there's 3 more equations that comes out of that one. And again, Q is the heat, M is the mass, C is specific heat, and delta T is the temperature. Now, the units. Most of the time, we'll be measuring Q in calories, little c calories. M will be in grams, and C will be in calories per gram degree Celsius, and your delta T in degrees Celsius. Now, the table they give will show this also in kilograms, kilocalories per kilogram degrees Celsius, and it'll be exactly the same number because that's 1,000 calories, that's 1,000 grams. So you can either do big measurements with it or small measurements with it. We're going to be doing mostly small ones, okay? Now, I think that gets us down to example 4.5 on page 97. And I guess we might as well go and erase these. If we need them, we'll write them down again. Sorry about my throat. The cold was getting better every day this weekend. This morning I woke up, had the best night since I had the cold. Everything was looking good. I taught my first class and my throat started hurting like crazy again, so too much talking. And then today I don't know what it's going to be like. Oh, all right. Example 4.5. How much heat? So what are we looking for? What represents heat? Q. This is your unknown here. Must be supplied to a 500.0, I've got hiccups now, gram pan. What's that a measure of? Mass. To raise its temperature, what's the change of temperature?
20 degrees.
Okay, yeah, but what is a change of temperature? What symbol? Oh, sorry. Delta T. Delta means difference. And what is your delta T there if you're going from 20 degrees Celsius, 20.0 degrees Celsius, to 100.0 degrees Celsius? What's that delta T? 80.0 degrees Celsius. If the pan is made of iron, okay? I'm just going to put Fe because that's the symbol for iron. Okay, now they haven't told us about the table yet. I mentioned it. If you flip over one page to page 98, you'll see this table. I may have to go get some water, but let's see if I can make it. Specific heat of selected substances. Air itself has a pretty low specific heat, 0.17. Aluminum, like we saw before, 0.22. Concrete, that wall right there, would be about 0.16. Copper, 0.093. We saw that on the figure before. Gold, I have glass, I've left that up. I'm not going to hold this up. I'll leave it in the tray here. Glass, on average, because of different quality of glass, about 0.16, a lot like concrete. So the concrete wall and the glass are, to change the heat, is right about the same specific heat. Gold, 0.03, which is one of the lowest listed. Ice, now look at ice. Would you think it had a high specific heat? It truly does. Higher than anything else mentioned. 0.5, calories per grams degrees Celsius. That's just to warm the ice, not to melt the ice, to warm the ice. Iron is 0.11, that's down there, less than air, less than concrete, less than glass, but more than copper. Lead, 0.0305, just barely more than gold, okay? Mercury, 0.033, that's just barely more than lead. Seawater, whoa, look at where it went to, 0.93. The very highest so far, almost twice what ice is. Silver, 0.056, just a little bit more than mercury. Soil on average, because there's different kinds of soil, about 0.2. That would be down there in the same range as air. Steam, 0.48, almost the same as ice. Steam and ice, opposite temperatures, it doesn't matter. Very high specific heat. But then look at water. One, and why is that? How did we define, what a calorie was? It was the amount of heat to raise 1 gram of water 1 degree Celsius, so therefore it has a specific heat of 1. Just about the highest specific heat of any common material on the planet. Now, what are some ramifications of that? Especially for you guys who work on cars. What do you use to absorb the heat produced by your engine by all that internal combustion?
Water antifreeze.
Yeah, you use water. Why do you put antifreeze in it?
To raise your boiling point, raise your freezing point.
And do what?
To lower your freezing
Okay.
point.
Yeah, the name antifreeze means it lowers the freezing point. That's the main reason. And it also raises the boiling point, you said too, right? Somewhat, okay? That's one reason. What else does it do for you? Some other good that it does for you. Some additives they put in antifreeze.
Keep from rusting.
Yes, it's an anti-rust protection as well. If you just put water in there at very high temperatures, you're going to be rusting your system really quickly. So not a good idea to use just pure water. One, you may burst pipes when it does freeze, like tonight, 22 is tonight, that's 10 degrees Fahrenheit below freezing. I hope that camper has pretty good heat. Oh, good, okay. That's going to be pretty chilly. If you didn't have antifreeze in your water in your vehicle, you're probably going to be, you can even, remember we talked about how powerful the expansion was, freezing water. It bursts pipes. Can it also crack a head? That is a huge chunk of metal. It can crack that head. You don't want to not have that. But the other thing is also prevents the rusting. Well, why wouldn't you, since water does cause it to rust some, why not use pure antifreeze? It doesn't absorb heat as well as water does. You better have water in it, okay? Because water has the highest specific heat. Now here's another ramification of that. What is the longest day of the year? Sunlight day.
The summer solstice.
Say again?
Summer solstice.
Summer solstice, which is around
Like June.
June 21st or so. Shortest day where you have the least amount of sun? December 21st, 22nd, somewhere around in there. So does that mean typically your hottest day of the year is going to be around June 21st? No. Hottest day of the year is usually July or August. This year it seemed like it was September or October, but that was a freaky time. Actually, over in Georgia, my brothers were telling me they had either 5 or 7 consecutive days in May when it was over 100 degrees. And the record before then, 1 day in May, ever. That's all they had ever had. And this year they had, I don't remember if it's 5 or 7, but it was multiple days. Weird year. Very weird. But no, and is the coldest day of the year typically December 21st? No, it's usually sometime in January or February. Now, why do you reckon that is? The most energy was absorbed by the Earth in the northern hemisphere, southern hemisphere, everything's reversed, on those days, and yet they're not the hottest or the coldest. What covers most of the surface of the Earth? Water. And water has such a high specific heat that you have to have it takes a long time for that water to cool down. Even though it's getting less energy from the sun, it still is going to take a while for it to cool down in the wintertime or warm up in the summertime. So that's why there's always a delay, typically, in what are max temperatures. Water has a very high specific heat. So, all that on the table, let's go back and get the specific heat for iron. C for iron, Fe, is what? From your table. Anybody? 0. Anybody? I can't hear. Anyone? Specific heat of iron. 0.11. What units? You have to go to the top of the table.
Calories.
Yeah, we're going to use the calorie one. Calorie per gram degree Celsius. Okay. What formula do we use to get Q? Oh, that was a long time ago, wasn't it? We just had it a few minutes ago. Okay, yeah, let's get it. M, what'd say? C, delta T, you got it. So what's your mass? 500.0 grams times C, 0.11 calories per gram degree Celsius. And what's your delta T? Second? 80.0 degrees Celsius. Okay? This gram cancels that gram out. These degrees Celsius cancels that one out. And you're left with calories, which is exactly what we want Q measured in, calories. Someone do the math there. 4,000 what? 400. What number? What unit? Calories. Now, if you wanted a bigger unit with a smaller number, that would be 4.40 probably kilocalories. But we're happy with calories. Okay? So there's the A part. Or the first part. Go back and find our problem. Here it is. Yeah, A part. Yeah, there we are. The first part of A. If the pan is made out of iron. Okay? What if it's made out of aluminum? So the Q for aluminum is going to be the same formula, right? And we're assuming it's the same mass of a pan. They didn't say any different. It said a 500-gram pan. What if that 500-gram pan was made out of aluminum? So the mass is still 500.0 grams. So what's specific heat for aluminum? 0.22. What units? Calorie per gram degree Celsius. And what was the change of temperature? Same 80 degree change of temperature from 20 to 100. And again, the grams cancel out, degrees Celsius cancels out, and what do you wind up with? 8,800 little c calories, which would be the equivalent to 8.80 capital, well, let's call it kilocalories. I'm not a nutritionist, so I don't go with the capital C that much. All right. That was the second part of the A. Okay? Specific heats. Oh, I'm sorry. I thought there was a... Yeah, the A part was iron, the B part was aluminum. In the solution, they had C in parentheses. I thought they had a third part, but that was C for specific heat. So sure enough, we got 4.4. Now, why did they only use two significant digits? Because specific heat was only in two significant digits. So I was putting 3 in. It's only 2. 8.8 and 4.4. Okay. Probably be better if I erased them rather than squiggle through them. Okay. Okay, that's better. All right. Make sense? All right. So it takes twice as much heat to warm the aluminum pan as it does the same temperature range as the iron pan. Have any of you ever wondered why that cast iron pan cooks so fast and so well? It's iron. Aluminum pan going to take a lot longer to heat up. Okay? Good deal. Let's move on to example 4.6 on the next page. I hope I can make it through. What is the specific heat? This time, what are we looking for? And what symbol is that? C. Here's the unknown here. What is the specific heat of a 2 kilogram metal sample? What's that a measure of? What do we measure in kilograms? Mass. Okay? If 1.2 kilocalories is needed, what is that a measure of? Heat, and what's the symbol of that? Say again? What's the symbol for heat?
Q.
Capital Q. Okay. If 1.2 kilocalories of heat is needed to increase the temperature from 20 degrees to 40 degrees Celsius. So what's that a measure of? That's your, to go from there is 20 degrees Celsius, and that's your delta T. Okay? Now, the question is, do you want to get your original formula and adjust it for C, which I did for you earlier, or do you want to use the formula we used last time, plug in the numbers, and then adjust for C? Either way, you choose. Second? Which one? Which? Adjust the equation. That sounds good. Give me the equation. Q is equal to MC delta T. If you're solving this for C, what would C be? Q divided by M delta T. So let's plug and chug then. Q is, there it is, 1.2 kilocalories. Your M is 2 kilograms. As long as everything's in C, you're okay. In K's, kilos. And your delta T is 20 degrees Celsius. Okay? I'm so sorry. So 2 will go into 1.2, 0.6 times. And 2 will go into this 0.3 times, and into that 10 times. And that looks like it's going to be approximately 0.03 what units? Kilocalories per kilogram degrees Celsius. Now, what material might you have there?
Gold.
My goodness, get out of downtown in a hurry. You are a rich man. Because 2 kilograms of gold is about 4.4 pounds of gold at hundreds of dollars per ounce.
About $500-$600 an ounce.
Huh?
It's probably about $500-$600 an ounce.
Yeah, it may be $500-$600 an ounce now. And that would be, ooh, goodness, the numbers just get huge, don't they?
Yeah, probably wouldn't have to worry about coming up here next class.
What's that?
If I had that much gold, I probably wouldn't come here next class. I'd probably just,
You wouldn't?
I'd take it.
Not even just for the benefit of our presence? The opportunity to be here together learning something? Oh, that hurts to the core. All right. About 0.03 calories per kilogram degrees Celsius. Now, they have a nice little blurb here on concepts applied on kitchen physics. Consider the following information as it relates to the metals of cooking pots and pans. Goodness gracious, my throat hurts. It is easier to change the temperature of metals with low specific heats. The lower specific heat, the easier it is to change the temperature. It is harder to change the temperature of metals with higher specific heats. So look at the list of metals, add the specific heats in the table above, and answer the following questions. Considering specific heat alone, which metal could be used for making practical pots and pans that are the most energy efficient to use? Notice they had the term practical in there. So I'll tell you now, eliminate gold. Not practical. Yes?
Gold is $1,470.95 per ounce.
Oh my goodness. Now multiply that by 16.
That's $47.29 a gram.
Okay. Wow.
So a kilo is $47,000. $47,292.14.
Okay, and how many kilos did we have last time?
2 kilograms.
It was 2, second? 2 kilos.
That's almost $100,000.
Oh, yeah. Oh, you wouldn't leave us for that, would you? Oh, yeah. Don't answer that question.
About
Okay.
95,
What's that again?
95,000, about a little less than $600.
Wow.
95,500.
Okay. Dream on. Okay. So eliminate gold, it wouldn't be practical. The next lowest, I thought it was silver, but no, lead. Would that be practical? Why not? Okay, yeah, it's a carcinogen. You don't want to cook in lead. Okay, it's also very heavy, very dense. Okay, next would be mercury. Why not make your pans out of mercury? Not only that, it's a liquid at normal temperatures and pressure, and if you use it to cook in, it's really poisonous then because it's a liquid. Okay. Next lowest is silver. Still not very practical. Way too expensive. The next lowest, what you see? Hiccups badly. Copper, isn't it? Hey, you see some of the really fancy stuff? that have the copper bottom about that high, and then it's a stainless steel above that? That's why. That's very efficient cooking stuff. Okay? Which metal would be used for most practical pots and pans, most energy efficient? Probably copper, at least the base of it. Again, considering specific heat alone, would certain combinations of metals provide any advantages for rapid temperature changes? I don't know really what they mean by that, but copper on the bottom and the stainless steel on top would be pretty good. I don't know what they're getting at there. Okay. Anyway, any questions on specific heat? One of the things we'll be dealing with today's lab. Okay. There's your formula. All right. Next subtopic here is heat flow. There are three mechanisms for heat transfer due to a temperature difference. Now, this is a temperature difference. We're not talking about other differences. The first of these is conduction. I'm not going into detail now because the next several slides will do that. After that is convection, and then you have radiation. Now, here's what they say, and it's very true. Natural flow is always from high temperature regions to cooler temperature. It's always that heat goes from hotter regions to cooler regions. Now, I can remember my dad saying how many times in the summertime, close the door, you're letting the cool out. Never heard that before, did you? Afraid so. Okay? What were you really doing? Letting the heat in, because natural flow is always from higher temperature to lower temperature. You're not letting the cool, you're letting cool air out. Really what's happening, heat flows from high to low. Just about everything. Next chapter we'll see one little exception to this, and it's really not an exception, but when you're talking about energy changes, you go from high potential to low potential, always, okay? Heat goes from high to low temperature. So, let's look at each of these separately. First, conduction. Conduction is heat flowing through matter, okay? Now, let me add a little something here. Predominantly solid matter. Doesn't have to be, but most of the time it is. Conduction is heat flowing through solid materials. Now, what's the mechanism here? And let's show the graphic here. If you put the Bunsen burner under one end of this metal pipe, and along the metal pipe, you have different thermometers there. At first, before you turn on the heat, they're all at the same temperature, whatever that is. But you turn on the flame, and this thermometer will get hot fast first, then that one, finally that one. Maybe it hasn't reached it yet, but at some point it will. Now, after a while, the whole pipe will be the same temperature. But initially, you'll see that kind of gradient. What's going on there? Well, in convection, the hotter atoms, the ones that you heat up here, they bounce more energetically against the other atoms. And that makes the next one bounce more energetically against the next one. They're losing energy as they go, but they're doing that. So what you're measuring with temperature, remember, average kinetic energy of the molecules. And these have more kinetic energy, these have less, these have less, these have even less. Okay? So that's why the temperature goes down like that. Okay, transferring some of their energy. They don't transfer it all, they keep some, but transfer some. Direct physical contact is required. Okay? If you had a gap here, you're not going to get heat transferred across the gap. You have to have the metal touching metal. Okay? and it certainly cannot occur in a vacuum. You cannot have, because you have no atoms in a vacuum, okay? So this only or predominantly occurs in solids. Now, what are your poor conductors? They're called insulators. And some of the best insulator or porous conductors are styrofoam. That's why a lot of your coffee cups you get at the fast food places, styrofoam. You'll see that's what we're going to be using in the lab today to store water and ice and things at different temperatures, because it doesn't conduct the heat through it. Okay? Wool. Now, I don't have on anything wool. Any of you have wool on today? It's a nice day for wool. But it's sort of like, actually that looks like, this is close to being flannel. It's not quite flannel, but it's close to. What's the advantage of wool or flannel or something like that?
Keeps the heat in.
It's what?
Keeps the heat in.
Okay, how? Because it contains fibers that are separated slightly from each other. It traps dead air, and air is a very poor conductor of heat, a very good insulator. But it has to be dead air, not air that can move, but air that's stationary. And that's why flannel or wool is so good, okay? Fleece is good, okay? I'm guessing that's fleece.
I don't know.
No, okay. But a sweatshirt, you know, it has fleecy-like materials in it. Something like what Thomas is probably wearing too. Pretty good air traps in there, isn't it? That's why it's a good insulator, keeping the heat inside. Okay, here is a table of sample conductivities, how well it conducts heat. This is just a few, okay? Silver is the very best conductor of heat. It's a 0.97 relative conductivity. I'd say let's go to the table in your book. It's more extensive than this one. Copper is number 2, very close to silver at 0.92. Now these are relative to each other. Aluminum is next at 0.5. Okay, we haven't even gotten down there. So look at that. Silver and copper way up there at 0.92. Aluminum down here at 0.5. Iron then down here at 0.11. Wow, what a change. Okay. Lead down there at 0.08. Concrete at 0.004. Glass at 0.0025. Tile at 0.0016. Brick at 0.0015. Water at 0.0013. Wood, 0.0003. Cotton, flannel, okay, 0.00018. Styrofoam, the one they mentioned here, oh, there's water and there's styrofoam. And that's 0.0001. Sorry. Glass wool, 0.0009, four zeros and a 9. Air, look at what it's down to. 0.00006. That is a terrible conductor and excellent insulator. And then finally you have vacuum, which is absolutely zero. No conduction at all through a vacuum. Okay? Now, can anyone remember any products? Now, I don't know if you'll remember these or not. Any of you ever heard of a thermos bottle? Yeah. What do you use it for?
Soup or coffee.
Okay, what does it do for coffee?
Keeps it warm.
It keeps it warm. And a thermos bottle, the old original ones, have you ever looked inside it?
Usually like a silver lining.
It looks like a silver lining. Now, actually what it is glass, but you can see through the glass there's silver on the outside. And the reason for that, it reflects the heat back. It's not so it conducts. Silver's a great conductor. You don't want it to get there. It has glass. But before it gets to the glass, you also have, do you know what's outside the silver? You got a metal casing with either air in that, so it's a terrible conductor, or some of them may have actually, some of the early ones they called vacuum bottles, because they actually pump the air out of them, making it almost a really, really, really good insulator. Okay? Now, not only did that keep your coffee hot, it would also keep your ice water very cold. Did you ever use it for that?
No, I just used it for like soup if it was going on.
Yeah. In the cold weather when you wanted it kept warm. If you had gone somewhere else in the summertime, you could have put ice water in there and it keeps it. Have any of you ever heard of the product? See if, what is the name of it? They make the chests and also the container. Oh my goodness, I can't remember. My wife has one.
Yeti?
Say again?
Like Yeti? Is that it? 'Cause I know they make pros.
Yeah, it's an unusual name. Yeti.
Yeti.
Yeti. Is that it? Yeah, Yetis. The Yetis. Boy, they will keep ice water icy, even in a hot cab of a car. You forget and leave it in there, and it gets real hot in the summertime. Go back, still ice water. Okay. I don't know what they've done to it, but they really insulate well. Those things are really heavy, so it makes me wonder if they don't have a vacuum somewhere in there, because they really keep it. This old glass they call single pane.
Yes, so.
Okay, not a very good. It's a pretty good conductor, not a very good insulator. But what do they use in most houses today?
Dual pane.
At least dual pane, and
Sometimes you say triple pane, but that's expensive.
that's really, really expensive. But the dual pane, they just are mostly using now, because what's in between that? Either something close to a vacuum or dead air. Now, sometimes they actually pump that full of argon, which is a gas that doesn't react with anything. So you won't get any mold, mildew, moisture, anything else in there. But even if you just have dead air space, that's a better insulator than single pane glass. So the table in your book has a lot more. Before we get to convection, there is a figure in the text, and the guy's up in the attic doing what?
Installing insulation.
Yeah. And what is that insulation? They give the name of it there.
Fiberglass?
Fiberglass. Now, I didn't see fiberglass in the table here, but it's something probably in between styrofoam and glass wool. But that's not the important thing of fiberglass. The important thing is, notice how thick that stuff is. Yeah.
And it flexes.
And yes, what were you just saying?
It flexes like you push it down and put more per square inch.
But you don't want to. You want to keep it like this. What? It has dead air. No matter what that's made out of, you want as much air in there as possible. That's why it's spongy like that. See, the glass wool will settle out. That's what's in our attic. We're in a 1930s house. And the glass wool they put in there over time has settled down. I've gone back and put in above our bedroom anyway some bats of fiberglass, because that will keep it. It's a much better insulator. And I want you sometime when you've had a real heavy frost, or snow, either one would work. Drive through your neighborhood and look at houses. And the houses, now, look at only the same side. If that side of the road, the houses are facing south and this side they're facing north, these are going to win every time. But look at the same side. Of all the houses, you can tell which ones have the best insulation. Those that keep the snow on it the longest or the frost on it the longest. Now this is excluding shade from trees. That will mess things up too. But as long as they're both in the sun or whatever, the ones that keep the snow the longest, they have the best insulation. And here's something else to notice. Do you now, or have you ever lived in a house where there was a family room added on the end that really was probably originally your garage? And they converted that to a family room or a den or some bedroom or something. You have seen those houses? Look at those roofs after a frost or a freeze or snow. Quite often you'll see those rooms lose the snow first, because garages are typically not insulated. And if the builder that converted it didn't go in there and add insulation, those are going to be the draftiest, and also in the summertime, the hottest rooms, because they didn't put insulation in. Now, a good builder would have put insulation, but we had our screen porch closed in, and that's one thing I forgot to tell the builder, and I thought of it when I was going home that day. So I got to remind John to put insulation in before he puts the ceiling, because we got some, not super expensive, but it was pressed aluminum, so it was really attractive looking, and that's what he was going to put on the ceiling instead of plywood. And I got home and he had just finished putting up. I said, John, did you happen to think of putting insulation? And he said, man, I didn't even think of that. And sure enough, every snow or heavy frost, you look out the back window, the den over here, snow stays there. The sunroom, it doesn't. It melts the fastest. Both facing north, so equal there. Okay. In fact, this one's more shaded than that yet. And yet you lose it. All right. There is a Science and Society question here. It says, can you spend too much for home insulation? And it talks about plus and minus of how much you spend and how much benefit you get. It's pretty interesting to think about. And here's another. Touch temperature. This is concept supplied on that same page 99. Some are objects that have been in the room at a constant temperature for some time should all have the same temperature. And this is going to be the last part of our lab today. Touch different materials and see what you get. Okay? Let's go back to the table here. Remember, the table in your book listed wood at way down there, down here near air, well, near styrofoam. It was between water and styrofoam. Air was. Wood was. Yeah, exactly in between water and cotton. Yeah, and cotton's just above styrofoam. Wood is a pretty good insulator. That's why some of the old pots that you would have that you cook with had wood handles, because the metal handles would burn your hand unless you used a mitten or something like that. Pot holder, okay. Think what you call it to hold the pot holder, okay? Because that had air in it, spongy, okay? But those old wood handles, you could just grab it, you wouldn't need a pot holder. Okay. Now, is our high school football playoffs still going on, or are they finished? Still going on. I don't know if your school was ever involved with any. I hope so, maybe. But you were probably on the field and not on the stands. But at those, if you ever went to say, the visiting field, and there you had some nice new looking, about this time of year, nice new looking aluminum bleachers, looked really in good shape, but then next to it were some older wood bleachers. Where would you sit on a night like tonight?
I'll probably sit on the.
Why?
Stand,
Huh?
because the aluminum will be real cold.
Hey, they're both out there in the same temperature, they're at the same temperature.
Metal just gets really cold, wood just kind of stays.
Well, here's why.
What's a better,
The metal, say again?
what's a better insulator?
Well, wood is a better insulator. So when you sit down on the metal, the aluminum bleachers, they have a very, look at that, 0.5, okay? Really good conductor. You set your tush on those, and they start conducting the heat away from you as soon as possible. And you're feeling pretty close to air temperature. Sit down on the wood, it has a conductivity of 0.0003 as opposed to 0.5. Much worse conductor, good insulator. You sit down on that, it's rapidly coming to your body temperature. So yeah, it feels warmer, but it's because it's not conducting your heat away from you. It's keeping your heat under you. Yeah, I would sit on the wood too. Even though they're old and decrepit looking, this time of year, the wood. All right. Now, let's move to convection. Convection is energy transfer through the bulk motion of a hot material. Now, what kind of materials would have motion in their bulk? Solids? No, solids are those fixed crystal structures. Their molecules don't move. This would be primarily fluids, liquids and gases. Okay? Convection is energy transfer through the bulk motion of hot materials. The only place you have bulk motion is in gases and liquids. Okay? These are not the very best of examples, but a space heater. Okay? What they call the convection heater. Now, some space heaters have fans. Okay, obviously the fan's blowing it. But if you have one of those that just has the elements in there, but no fan, then what's happening with that, and this was also back when I was in grade school, mostly, we had those old things that sat usually under the windows. Radiators. They just pumped hot water through them. Okay, that's all that was happening. And what would happen, no one was blowing anything, but the cool air at the floor would go through those and be heated and go to the ceiling. And then cool air, and that was what warmed the room. Because you had the circulation, that's called convection. Okay? So to me, the old radiators were the better example than a space heater. Now, my grandmother and my great aunt both had houses with what they called floor furnaces. The furnace was down there under the floor in what you would call the crawl space. And you turn the furnace on, and there was a grate up here on top, and the heat came up. No fans, it came up. The house I grew up in, my dad finally got around to installing a wood stove down in the basement. And it was in the room where my uncle has designed the house. It was the fallout shelter, because this was back at the time when everybody was afraid of the atomic war between the Soviet Union and the U.S. So people were building fallout shelters. Really well contained space down there, you know, and he put we weren't planning to use it for fallout anymore, so he put his wood stove down there, okay? And all they do was close all the doors to the outside, leave the stairwell doors open, and that wood stove, oh boy, it heated up that room in the basement like crazy. That heat came right up the stairs. That's convection. Okay? And when they say gas furnace forced, a forced air furnace really isn't true convection. That gas furnace that was down there, that was just a floor furnace, that would be convection. Now, natural convection mechanism is this. When you heat molecules of a fluid, that's either a gas or a liquid, they bounce around each other and they get further and further apart because they're bouncing with more energy, forcing each other further apart. That makes them less dense. So they rise and the cooler molecules move down. Now, and that's where you get what they say, hot air rises. Okay? There's another name for this that they will use quite often in buildings. It's called the chimney effect. That's what they use the stairwell for. That's why chimneys work. Look how, unfortunately, in a fireplace, most of the heat is going up with the smoke. It goes right up the chimney. But you get some heat coming out, and wood is plentiful, cheap. And actually, wood is a great heater. You've heard this before, haven't you? Wood heats you twice as well as just about anything else. Because it first heats you when you're cutting it, and then it heats you when you burn it. Okay, but that's a different story. Okay. Have you ever done any splitting of logs? Or, yeah, it get quite warm. All right, but anyway, hot air rises. Chimney effect. Do any of you remember, I doubt if you do any of you remember the cookware that came out with called Visionware? It was sort of an amber-colored glass, but you could cook in it. It wouldn't break. And it was pretty thick glass, so it wasn't all that great of a conductor. If you think back to the conduction slide, glass wasn't that good of a conductor. Did they even list it on here? Yeah. It was not particularly great. The metals are much better. But you could see it. And my mom had a set for a while. And when you put it on the stove, you could see the middle of the pot. That's where the boiling would happen first. And you would almost see the currents doing this in the pot. The middle was the hottest part. The edges, because they were exposed to the air, was the coolest. And you would see that liquid circulate. That was convection. Hot air or hot fluid rises, the cooler fluid sinks. Okay. Here's that good old radiator. Okay. The heater is over here. All these veins will let the air go through. The cooler air comes in the bottom, it heats up in here, goes to the top, and then goes back and around. Several winters ago, we were repainting what had been my wife's parents' lake cabin. And they had built it with really high vaulted sort of ceilings. And I was up there painting near the top and coming back down. It was miserable doing that, because down here it was pretty cool. Up there it was burning hot. And it wasn't more than 10 or 12 feet difference, but all the hot air was rising. And then it would cool and move down, and it was many degrees cooler down here than it was up there. And that's why they recommend you use a ceiling fan in the wintertime. You might want to reverse the circulation on it, but to blow that hot air down, and that way your thermostat is down around here. The hot air is up there. If you blow it down, you're more comfortable without using as much energy to heat all the air to that temperature. Okay. It's an okay illustration, but I think it has some limits to it. What if you had two invisible cubes of air, okay? Invisible containers of air. They have the same number of molecules in them. You put them on an even seesaw here, and they balance, right? Okay. Now, you heat up this cube. You still have the same number of molecules in there, but you just made the cube bigger. But it's still the same mass. Okay? Now get your original cube and just take an extract out of here, and what you have now is fewer molecules, but the same volume, and now the cool one is heavier, the light one is lighter. That's the mechanism here. Okay? Hot air rises, cool air sinks. Okay? Or any fluid, not just air. The third type of heat transfer, I think is what they call this, heat flow, is radiation. Now radiation, let's go back to those space heaters you have. Now some of them have fans, and that's what distributes. That's partly convection too. But others of them just have a coil there in the center, but then a really parabolic mirror behind it. And now that's heating you with radiation. Because the radiant heat, the heat coming off that coil, is hitting the mirror and bouncing off towards you. That's also what your fireplaces do. What you feel in front of a fireplace is radiant heat. Okay? Most of the actual heat is going up. The convection heat is going up the chimney, not doing you any good. But the radiant heat is coming out the front. And the back of a flue in your fireplace is usually slanted, so it does reflect it out a little bit. Okay? But radiant energy is energy associated with electromagnetic waves, primarily your infrared radiation. Now, where did conduction happen the best? What kind of materials? Conduction, solids. Convection, liquids or gases, the fluids. Where does radiant energy do best? They vacuum. Because the electromagnetic radiation travels best and easiest through a vacuum. That's why the energy from the sun reaches the earth. There's no solids out there. There's no air out there to speak of. It's all pretty close to being a vacuum. But the radiant energy makes it, the electromagnetic waves make their way to us. So it can operate through a vacuum. It can operate in air. It can operate in metals and liquids too. But it operates best in the vacuum or air. Best in the vacuum. All objects either emit or absorb radiation. Okay? Remember, I think I talked about the patio we dug out behind the house. We put, they call it rubble, stone. I think we're mined around probably Aniana, Alabama. There, we built a stone wall back there. Now that faces south, okay? And the southern sun comes in and hits that, and it warms up those rocks. And then in front of those rocks, it stays much warmer than it does against the house, which is facing north and doesn't get that direct sun. And you can sit back there on a pretty cool day and you can tell the difference. You would think the house would be warmer, but it isn't. Hopefully we have better insulation in the walls there. Okay, but all objects emit or absorb radiation. And here's a general rule of thumb. Your best emitters are your best absorbers too. The typical physics name for it is your black box radiation. Because black usually absorbs heat, black also emits heat. Okay? It re-radiates. Now, no, in the summertime, when I was growing up, we didn't have air conditioning in the house. And I knew better than to sit next to my mom on the sofa. If I did, she was going to push me away. She said, "You're emitting too much heat. Get away from me." Because I was always hot-blooded, or always too hot. And my wife says the same thing. Move on the other side. Okay. All objects either emit or absorb radiation. Now, The temperature determines three things. The emission rate, the rate at which the heat is emitted. In other words, if you have a hotter body, it's going to emit faster than a colder body will. The intensity of the emitted light, now that's one form of radiation. We saw that, those who had Physical Science 111, that the hottest and the brightest stars give off more intense light, okay? So the intensity of the emitted light, and also the type of radiation given off. The very hottest of the stars are probably going to be a lot more gamma radiation than the really high energy radiation. Our sun is right in the middle. It gives off a lot, but not nearly as much. So I wouldn't want to be circling one of those super hot stars. You probably wouldn't be able to live around those. The temperature is determined by a balance between the rates of emission and absorption. And that's one reason we can live on the Earth. The Earth is so far from the sun, we ought to be too cold to support life. But because we have this nice warm blanket of an atmosphere around us, we absorb more than we give off. Now, the problem is, at least this is the theory, that as we put more carbon dioxide and methane into the atmosphere, we get better at absorbing and less good at radiating, and that's what causes global warming. Okay? And that's exactly what we're talking about here. The balance between the rates of emission and absorption. Right now, we feel like by putting more carbon dioxide in the atmosphere, we're emitting less and absorbing more, and that's why we're warming up. Remember, we talked about the greenhouse effect of your car. You know, the absorption through the glass is more than emission back out through the glass. So that's why greenhouse works. That's why your car warms up and stays warm in the, in fact, way too hot in the summertime and nice and toasty in the wintertime if it's a sunny day. So there's radiation. Conduction mostly through solids, convection mostly in your fluids, that's gases and liquids. Radiation best in a vacuum, but also goes through air as well. Now, that gets us down to section 4.4, which is energy, heat, and molecular theory. Now, how are we doing on time? We've been at it close to 2 hours now. Can you go a little bit longer? Okay. No. Have we been 2 hours?
No,
Huh?
Yeah, it's only like 5 or 6.
Yeah. Okay, so we've been going close, not quite 2 hours yet. So let's talk about energy, heat, and molecular theory. Remember, we started with molecular theory, and then we've sort of gotten away from that. Let's go back. There are two responses of matter to heat. Okay? In the first lab, we saw really both of these. Okay? Though we weren't really measuring that at the time. We saw temperature increase within a given phase. For instance, when you had the water on the burner, the heat element there, we had to keep talking until it started boiling. If you'd have had your thermometers in there, you would have seen the temperature increase while it was still water. But once it got to boiling water, the temperature quit increasing. It stayed right there. We also saw that when there was ice and water together, the temperature didn't change. Even though the ice was melting, the temperature remained the same. So the temperature increased within a given phase. There was a mixed phase. Ice and water, cross phases, no change of temperature. Hot water and steam, no temperature change. But if it had just the water within a given phase, add heat to it, you have temperature increase. Heat goes mostly into internal kinetic energy of the molecules of that water or whatever your substance is, And that is defined by specific heat. The amount of energy required to change the temperature 1 degree Celsius, 1 gram, 1 degree Celsius. That's specific heat. That's temperature increase. Change of temperature is specific heat. Now, here's basically what's going on there. When you have ice, now I don't really like this ice because they show a little puddle of water. I don't want it to be a puddle of water. I want it to be ice. Cold, cold ice. Okay? The only activity here, you're in the fixed crystal frame of ice, and the only activity you have is the motion of the molecules. It's still within the phase, one phase. Okay? If you add heat, you warm that ice, but you don't melt it. Okay? If you take heat away from it, you cool the ice down below the freezing point, and it just keeps getting colder. Now, I can remember I did some graduate work at the University of Nebraska-Lincoln. You talk about cold. There was one Christmas I rode home with a friend of mine, and we didn't bring a cooler. All we did was put our drinks, the aluminum cans, next to the windows. Had the car pretty well packed. Put them right next to the window. They so cold you could hardly drink them. Okay, that was cold. But as we were coming down, it had been snowing up in Lincoln, and about the time we got to Kansas City, it was freezing rain. And the freezing rain, let's go back up to Lincoln. The wipers were working fine because the ice would hit the windows and it wouldn't melt. It wouldn't stay on there, so it just moved. Once we got down around Kansas City, now the windows were warm enough and there was a little bit of moisture and stuff like this that would hit the window and immediately change the ice. And then the windshield wipers weren't working because they were ice. So you had to have your defrost on that. But before that, and also before that, when we were on the road and that snow was packed, it was okay driving because it was so cold that it wasn't compressing it and making it change to water and then change to ice. It was just blowing right off the road. When we got down there in Kansas City, as soon as you ran over it, it became ice, and now no traction at all. Miserable driving. Okay. Now, when the ice starts melting, like they're showing here, some of those water molecules are breaking off from the crystal structure and now are liquid. Others are still solid. Okay? So you have a combination of both of them going on. Now you just don't have vibration, you have rotation. The water molecules are free to move past each other. You keep adding energy to it. This is when you get the water to a boil. Now it takes off and becomes gas and doesn't condense again. While it's boiling, you have liquid and gas phase, and then they'll all be at one temperature. Okay? This will be at one temperature. You got both ice, solid water, and liquid water here. But this one, it's all gas. You can just heat that up, and now you have temperature increases. So you have temperature increases only when you're within a given phase, and you don't have the cross phases there. Okay? Now, the terms, here we have Mendez. Okay. So we're only missing Ryan and Latricia. Okay. Now, Ryan usually comes in after they finish with his grandparents' furniture. I think he said his grandfather died recently, and now they're having to clean out the house. And if you've ever done that in an old house where people have lived for decades on end, it's a job. It's a big, big job. Okay. So what we have here, if this ice is melting, that's absorbing energy and changing phase. Here it's absorbing energy, still changing phase, Here's absorbing energy and increasing temperature. Okay? Increased molecular potential energy happens as you put more and more energy into it. Energy is released, then you're going from gas phase, as in steam, and this gas, say you have a glass of ice water here, you have a lot of steam or air, or water vapor in the air, what happens to the outside of the glass? I'll talk about this a little bit later, but what happens to the outside of the glass? You get water on it. That's from condensation. That's when this water here is coming out of and changing phase back to the liquid phase. Okay? And then you keep dropping energy, and now it's condensation going this way, freezing going this way. Okay? As you're removing energy from it, more and more of the water freezes to ice until it all becomes ice, and then it drops in temperature. Okay? I think that covers everything there. So, go back and reiterate this. If you're within a given phase, either all solid, all liquid, or all gas, you add more energy to it, you increase temperature. You pull energy away from it, you decrease temperature. That's when you're all within one phase. The heat goes mostly into internal kinetic energy, which they're not talking about with that one. Okay. Now, I don't know what was supposed to have been there. The second response of matter to heat is a phase change. Okay? At a constant temperature. Okay, here's the difference. When you're adding heat, when you have two phases present, then the heat goes into changing the solid phase to the liquid phase. You don't change temperature, you just change phase. Or you're going from a liquid phase to a gaseous phase. That's like the water boiling. You don't change temperature, you change the phase. That's related to changes in the internal potential energy. That's the potential energy of those molecules holding onto each other in the solid crystal, moving around each other in the liquid, or freely moving in the gaseous phase. That's when you're changing those internal potential energies. That heat is called latent heat. Now the term latent comes from some Greek or Latin or somewhere that means hidden. Hidden heat. And that's when you add heat to a substance and it doesn't change its temperature. Like you add heat to ice and it stays ice. What you're doing, adding heat to ice and it starts melting. You don't change the temperature, you just change the phase. Or you add heat to the water and it doesn't change temperature, it's just more of the water becomes steam. You're changing phase. You don't see a change of temperature, so it's hidden heat. All you see is a change of phase. Here is a diagram that shows that pretty well. If you have, now this is ice, this is water, okay? If you have ice down here at minus 20 degrees, okay? That's cold ice. That's really cold ice. Now this is Celsius too, not Fahrenheit. It's Celsius. Really cold. You add heat to that, you do not melt the ice. You just warm the ice. Okay? And it warms according to the specific heat of ice. Does anyone remember what that was? 0.5. Pretty high specific heat. But that's 0.5. Is calories per gram degree Celsius. All you're doing is warming the ice. When you finally warm it up to 0 degrees, the melting point of ice, then it starts melting, but it doesn't change temperature because now it's two phases. You got solid phase here, liquid phase there. So it starts melting and does not change temperature until all the ice melts and all of it becomes liquid. When that does happen, now you're all liquid and you add more heat, now it starts warming it again. Does anyone remember the specific heat of water? Remember this one. 1.00, okay? Specific heat of water. Just about the highest specific heat of any natural substance on the planet. It keeps warming and keeps warming until it gets up to 100 degrees Celsius. At that point, though, at normal temperature, at normal pressures, then it starts boiling. That's what was happening in the lab last time. As I put it on the heater, and it was, I put hot water in there, but it wasn't super hot. It just kept increasing temperature, until finally we saw it start boiling. What the boiling is it's changing to a gas. And that's what made the bubbles in it and made it boil. And then it's a constant temperature, 100 degrees Celsius, if our thermometers had been right, that would have been the boiling point. It stays that way until all the liquid becomes gas, and then you keep adding heat, and now you're superheating the steam. You're now just changing temperature. It's not going to change. We're not going to get up to a plasma, not with water, not for a long, long time. So you just continue warming it there. Again, back to specific heat. At this point, you're dealing with latent heat. At this point, you're dealing with latent heat. Here's specific heat, specific heat, specific heat. And whereas this is 0.5, this is 1, this is 0.48, the specific heat of steam. They're all relatively close. The latent heat of melting, or if you're going this way, it would be freezing, removing heat from it. If you just return this, you have steam here, and then you cool that steam, and it becomes a liquid. That's condensation. And it continues cooling, but doesn't change temperature until all of it changes from a water vapor to a liquid. Then it starts cooling the liquid, and that's a specific heat again. You keep cooling that liquid, then it freezes. Going this way, it's freezing, and that would be at constant temperature until all the water becomes solid, and then once it's all solid, you start cooling it again, specific heat again. Okay. So it goes both ways here. We haven't talked about what that latent heat of melting or freezing, or the latent heat of boiling or condensation is. We'll get to that. It's called latent heat of vaporization. So let's get to that. Well, here's first the graph that shows it. Okay? And here's the names for it. When you're going from a solid to a liquid, or coming this way from a liquid to a solid, we call that the latent heat of fusion. That sounds like it's going liquid to solid, but it's the same thing we pay going from a solid to a liquid. Okay, latent heat of fusion. When you go from a liquid to a gas, or a gas to a liquid, we call it vaporization. Well, no. When you're we call it the latent heat of vaporization, but the process is called condensation. This is the latent heat of fusion. If you're going that way, it's freezing. Coming this way, it's melting. Latent heat of vaporization, going that way, it's vaporizing or boiling. Coming this way, it's condensing. But you can also, under certain circumstances, go from a solid to a gas, or a gas to a solid. That is called sublimation. Solid to gas or gas to a solid is called sublimation. And it's called the sublimation point too, which we haven't gotten into. Can any of you think of a substance that sublimes at normal temperatures and pressures? Any of you been to rock concerts? No. They may do it at country music concerts too, I don't know. But I've often seen it. Oh, my goodness, the 10 o'clock scholar. All right, here's Ryan. And let's see, he made it in class time. Good deal. We're only missing Latricia again. Okay. Glad to have you all here. What I was getting at there, have you ever seen the concerts where you have all this cloudy, vapor-looking stuff around? You don't know what, you don't even know Not even seen it on TV or somewhere like that, where you have it looks like smoke. It isn't smoke. You know what I'm talking
I know
about?
what you're talking about. They can step on the thing and they can make it go themselves.
Yeah,
Step on the pedal and then it just goes.
right. You know what that is?
It's
Okay.
water vapor.
Well, what you're seeing is water droplets, just like you see in a cloud. But what's happening there is, has anyone ever heard of dry ice?
Yeah.
What is dry ice? Solid carbon dioxide. Dry ice. And it will immediately, when you remove the sub-freezing temperatures you have in the pressure and hit the pedal and expose it, then it immediately goes to a vapor. Goes straight from a solid to a gas. And when it does that, it's absorbing a whole lot of heat. And when it absorbs the heat, that changes the liquid in the water in the air into water droplets. Okay? And when it does that, you get the cloud effect. And that's what gives you all the effects. That when they strobe the lights and stuff like this, you see the clouds and all that kind of stuff. That's sublimation. We're not going to deal with that any at all, just to let you know it happens. So when the temperature direction is increasing, we call this the melting point at which you change from a solid to a liquid. The latent heat is called fusion. When you go from a liquid to a gas, that's called the boiling point. That's the heat of fusion. The latent heat is called the latent heat of vaporization. And when you sublime, you're going from solid to a gas, and that's the latent heat of sublimation. The process is sublimation. And then when you're cooling, it's also called sublimation, when you're going from a gas to a solid. When you go from solid to a liquid, that's called this condensation point. It's exactly the same temperature as the boiling point. Exactly the same. It's just the heat's going in the other direction. You're going from a solid gas to a liquid, condensing on your glass. And when you finally get down to the place where you start freezing, same temperature. Freezing point, melting point, same temperature. It's just that you're removing heat now and you're changing from the liquid to a solid. So that's coming this way. What we call those. Now, let's back up to here. Okay? Anytime you have a change of temperature, what kind of heat are you dealing with? I'll go back a couple slides. It'll show up at the bottom, right there. Specific heat. Anytime you have a change of temperature, that's a specific heat. Okay? The specific heat for ice is C for ice is 0.50 calories per gram degrees Celsius. The specific heat of water, C for W, water, is 1.00 calories per gram degrees Celsius. And the specific heat of steam, I'm going to put it up here, the specific heat of steam is 0.48 calories per gram degrees Celsius. Now, here we have latent heat. Anytime you're changing phase, that's the hidden heat. You don't see a change of temperature. It's all at a constant temperature. What is that? The latent heat for melting. And by the way, the formula for all these with this, remember from before, Q is equal to MC delta T. Or you can rearrange those any way you want to, right? Correctly. Okay? When you're dealing with latent heat, guess what you don't have? A change of temperature. So your Q is then M times L. Now it depends on what L you're dealing with. If you're dealing with the melting, that is the latent heat of fusion. So L sub F, you could think of that as freezing or melting, latent heat of fusion, for water. Now this is for water only, so don't get it confused with other things. This is going to show up in the table 4.4 on page 104. I've given the specific heats for those three, and they show up. They actually give an extra decimal place. I'm sorry. Okay. No, they only do. They only do 2 zeros here, not 3. Okay. Now, the latent heat of fusion, catch that. This is 80.0 calories per gram. Now, what are we missing there? These are all calories per gram degree Celsius, calories per gram degree. This is only calories per gram. Why? You have no change of temperature. There's no change of temperature. So if you put a 0 there, it wipes out the whole meaning. So then, that's why you have Q is equal to ML. Because M is measured in grams, and L is in calories per gram, so the grams cancel out, and that gives you Q in calories. So the latent heat of fusion is 80 calories per gram. But catch what it is for boiling. This is the latent heat, I can't write, the latent heat of vaporization, that's 540.0 calories per gram. You talk about a bunch of heat. That's why it took so long to get that water to boil. Number one, water has such a high specific heat, it took a long time to get it hot enough to boil. And then once it boiled, it took a long, I could have boiled all day long and not used all that up, because it took 540 calories of heat to evaporate 1 gram of water. That's a lot of heat. Okay. Now, so I've given the two formulas here. You have, it's only one formula. Q is equal to MLF or MLV. Depends on whether you're changing phase from solid to a liquid or liquid to a solid. So both of those are this one. Or liquid to a gas or gas to a liquid. They both use that one with those constants. Okay. Now, if you remember, okay, before we get to evaporation condensation, if you remember back when we were talking about passive solar design, and I talked about changing the elevation of the roof and various things like that, they have some listed here. It seems like it's kind of out of place, but it sort of does fit here too. Page 103, a closer look. Really a good blurb. It's a long blurb, but pay attention to it. Several features are listed there. The first one is just adjusting and using the radiative energy from the sun. And that's where, in the wintertime now, I go around and open the blinds so that in the daytime, the sunlight comes in and helps heat the room. At night, I close them up to add another layer of insulation, sort of dead air space to keep as much cold from coming in. Then they list a Trombe wall, which I had never heard of before this book, that actually does a better job of absorbing the heat from the sun and then re-radiating into the room. And then they show it's sort of like a sunroom. You have glass all around like a greenhouse, and you absorb it in and then let that come into the house if you want to warm up. If you don't want to warm up, close it off to keep it from coming in. Okay. Several passive solar designs. Okay. And then this graph that we saw here is done again on page 4, on figure 420. Very similar to the 418, but it has a little more detail. It gives the formulas in there. It doesn't give the constant values, but I put those around there as well. All right. And then the one other feature they show here when they were doing this on the table 4.4, which we don't show here, they also list again. And why they list it this way, I don't know. 1 kilocalorie is the same as 4,184 joules. If I were listing that, I would just say 1 calorie is 4.184 joules, or 1 kilocalorie is 184 kilojoules. I don't know why they put 1 as 1 and 1 as 4,000. To keep these two numbers close together would make sense. If I do want to go to joules, I just move the decimal 3 places. So, anyway. Now, before we get to evaporation and condensation, which is the next slide here, let's go back and find some white space. There's some white space, or brown space in this case. Let me clear what I've got here, and let's do, let's do example 4.7. How much energy, what's going to be the symbol for energy? Earlier we were calling a form of energy. Heat. And what symbol is that? Q. Oops, I can't write. Okay. Sorry. This is what we're looking for. How much energy does a refrigerator remove from 100.0 grams of water? Okay, and when they call it water, you think liquid, okay? What is that a measure of? 100 grams. That's your mass of water. I'm going to put W for water, okay? At 20 degrees Celsius, let's call that TI, initial temperature, okay? To make ice at minus 10 degrees, 10.0 degrees Celsius, I'm going to call that T final. Okay? T initial and T final. So how much heat does a refrigerator have to remove from 100 grams of water at 20 degrees Celsius? That's basically room temperature, remember. You just put that glass of water in, that tray of water into your freezer, okay? Room temperature water into your freezer, and you want to make ice at negative 10 degrees Celsius. What steps does that refrigerator or that freezer have to do? What's the first thing it's got to do? That water's at 20 degrees Celsius. What's the first thing it's got to do?
Make the water cold.
Make it colder. You got to chill the water. So if you're chilling the water, what formula are you using? I'm going to call this cooling. What formula do you use? First one we had. Y'all knew it back then.
It was mass times C.
MC delta T, because you have a change of temperature. This is specific heat. Now, what change of temperature do you affect when you're cooling that water? How cool can you get it? How cold can you make that water become?
32 degrees.
Say again?
32 degrees.
Which is, that's Fahrenheit.
Freezing.
0 degrees Celsius.
Say again? 0 Celsius. So your first stage gets you to 0 degrees Celsius. So what's your delta T there? I'm going to call this TF, for T for freezing. What's the delta T there? 20 degrees. So you got the mass. What was your mass of water? 100.0 grams. What's the C for water, specific heat for water? 1.00 calories per gram degrees Celsius. Now I don't have room, but I'll write it underneath it. And what's your change of temperature? 20 degrees Celsius, 20.0 degrees Celsius. Okay, now this degree Celsius is going to cancel that one out. This gram will cancel that one out. Multiply those together, and what do you get? 2,000 calories. Okay, which you could call, if you wanted a smaller number but a larger unit, 2.00 kilocalories. Because you see we got 3 significant digits at the least. So that's to cool the water. That is the Q sub C for cooling the water. What's the next thing you've got to do to that water? It's at 0 degrees now. What you got to do? You got that water down to 0 degrees. What you got to do with it now? What happens to water at 0 degrees? It freezes, so you got to freeze the water. What are we involving there? If you're changing phase, what's your formula? Q is equal to? What's that formula? Latent heat, that's M times L sub, and which L are we dealing with? Say again? LF, latent heat of fusion. The mass is still the mass. That's 100 grams. It just now happens to be very cold water. And you multiply that by, and what is the latent heat of fusion for water?
80 calories.
80.0 calories per gram. And again, the grams cancel out. You have no change of temperature, because a change of phase happens at the same temperature. So you have no change of temperature. What does that produce? 8,000 calories. Which, if you wanted to do a smaller number, a bigger unit, that would be 8.00 kilocalories. Okay. Wow. To cool at 20 degrees just took a fraction of what it takes to freeze that water. Now what do you have to do? One more step. That was when you went from water to 0 degree ice. This was water to ice. That was a change of phase. Now what do you have to do to that?
Get it down to -10.
Yes, you got to change the temperature again. So that's going to be the Q. This is Q freezing or fusion. This is Q for chilling the ice. This was chilling the water. This is chilling the ice. What formula do you use? MC delta T, because you are changing the temperature. The M is still 100 grams. It's just now it's ice. What's your C for ice? 0.500 calories per gram degrees Celsius. And I still haven't allowed enough room. What's your change of temperature? Yeah, okay. We're going to deal with positive heat even though you're losing heat. We just call it that. So we'll call it 10 degrees. Absolute value. 10.0 degrees Celsius. And when you multiply those together, what do you get? 500 calories. Now, if you wanted to, you could call it 0.500 kilocalories, but why? Let's just leave it calories. So let's add them together. How much energy did that refrigerating unit have to pull out? 10,500 calories. Or if you wanted to use a bigger unit, smaller number, 10.5 kilocalories. Quite a bit of heat. Now, I kind of disagree with how they put their decimals. They're showing 4 significant digits there. We only had 3.
545.
And it's 5:45. So that was probably a pretty good place to stop. Any questions on 4.7? Okay. We'll begin next time with evaporation and condensation. So let me put my paper in place here. Now, what we've got to go yet is evaporation and condensation. Then we'll do thermodynamics, and that's only a few pages, and then we're through. So I think next time in the first 2.5 hours, we'll finish chapter 4. Then we'll get started in chapter 6. Now, here's the deal. You were asking about, do we have a lab every time? I can't swear that we will, because next time we start chapter 6 and we finish chapter 4, start on chapter 6, and we've got to get at least through 6.2, I would say, in order to do our lab. So we, maybe not all of 6.2. We don't need to get into Ohm's law. Okay, so we'll only go part of the way through. I think we can manage that. So next time, we'll have 2.5 hours of class, finish chapter 4, get started in chapter 6, and if we get far enough in 6, then we'll stop and have the first lab for 6. Chapter 6 has 3 labs, so that means Thursday we'll have the first of those 3 labs. We still have class the following week, and I'm guessing at least one of those days we won't have a lab. Will be, well, I know that on Tuesday we'll have the test for chapter 4 of the last 30 minutes. So it may be that on Tuesday we do 4 hours of class and then 2 hours of test. 30 minutes of test. So it may be Tuesday. Is that the day that you need it, or what day did you need?
Yeah, 19th.
Is that Thursday, Tuesday, or Thursday?
Tuesday.
Tuesday. So that may be it. Now you might miss a test, but you won't miss a lab. Is that all right?
Yep.
Okay.
Test up.
All right, so that's, I'm guessing now, we may not pan it out that way, but we'll. Then when we come back from Thanksgiving break, we only have 1 week here. Is that right? Only 1 week?
2 weeks.
After Thanksgiving?
Yeah,
I
December
know
13th.
finals start on the 9th.
Okay.
December 9th is when finals start.
Say again?
December 9th is when finals start.
Okay, but you see, we have, after Thanksgiving, we come back right at the end of November, so we have 1 week of class, and then we have Tuesday of class, and then Thursday's our final. So we have a week and a half when we come back. 2 weeks, including finals, but of class time, 1.5 weeks. So we've got 1 lab in chapter 8, only 1 lab there. 3 labs in chapter 6. So we have, after today, 2, 4, 5 regular classes, and then the final exam's the last day. And we have 4 labs to do in those 5 days. So one of those days we won't have a lab. But there'll be plenty of time at the end to make it up, or you can get someone to get data for you if it just happens to fall. So we do. Because I'm guessing we're going to be ready for Ohm's Law Lab shortly. Maybe the electricity and magnetism not, but anyway, we'll see how it pans out. Okay. I'm going to end the recording. We're on number 1, page 1, Roman numeral 1. It says measure the temperatures of 2 half-filled cups of water, cup 1 and cup 2. Put cup 1 temperature by cup 1, cup 2 temperature by cup 2. Sort of make sure they come to equilibrium and they're settled out. Okay? Okay, everybody got the temperatures, 1 and 2? Don't get it all the way out of the water. Be sure you leave the bulb underwater when they're ready. Everybody got the temperatures and recorded them? Okay, yeah. Pull the thermometers out. Be very careful of the thermometers. And either pull 1 into 2 or 2 into 1, but only those 2. Yeah. Pour all of it into it. 1 into 2 or 2 into 1. Now put either thermometer back in. Okay? And put the other in 3 there. Okay, see what the mix comes out being. All of it. You got it. Which is this? Put the other thermometer at 3. Okay. Have y'all got the mix? Okay. Take the thermometers out. Take the thermometers out for 1 and 2 or 2 and 1. Okay. All right, you got your mixed temperature? All right, now get your, okay, everybody got the mixed temperatures? Okay, take the thermometer out of that mix and put it in the 4. Yeah, I did.
Oh, we already did 3 and 4.
Huh? We already did? Oh, wow, y'all are quick. What was yours?
This one we got 45.
Before we do the next step, I want you to estimate it when you mix 3 and 4, what will be its temperature. No, don't do it yet. Estimate first.
Oh, yeah, we
Oh, you already estimated. Okay? Then pour it in. All of it. All of it. And then put the thermometer in. And see what it is.
It's gonna be around like
What?
28%. I'm gonna say 28, so you can do the math.
You can do different
I
kinds of
did some math, I'm gonna
temperatures
think
if
it's
you want.
28, you're allowed to put what you want.
Okay, so either thermometer in the.
I swear, you're right. You're gonna put
Okay, now you don't read temperature out of the water, be sure you keep it in the water. Yeah.
No, it's not a mixture. It's like what?
Okay, you're doing E, the actual mix.
Get fired.
What's the estimation?
Yeah, your birthday, you're allowed to be in big room.
35, 31.
Yeah, we can make sure it's double right. Yeah, make sure you're right. Alright.
See what your temperature is.
No, higher than 300. Nope, it's going even higher. It's a third party.
Y'all made your edit.
It's a lot higher. It's still going. You're both higher.
Okay.
All three was coming through.
Have you made your measurement? Number E. Yay or nay? Got them? Okay.
It seems to get moved just a little bit.
Now, my question to you, you can just leave that there for now. Okay, my question to you. Number one, did your A and C, were those cups 1 and 3 and 2 and 4 pretty close to each other?
Yes.
Was B and E pretty close to each other?
No. Similar-ish. Yes.
Why not? If the temperatures going in were close, why is the temperature coming out not close?
The volume of water added.
Very good. Actually, rather than volume, the mass of the water, but it's the same deal.
Ours are pretty
Okay.
close.
Huh?
Yeah, ours are pretty close.
Really?
So we had 45 for C and then 37 for
Okay, no.
well, we.
No, these two are close, right?
Yeah.
Or are these two close? Kind of, but not as close as these. These are 1 degree apart, and these are 7 degrees apart. And these are degrees Celsius, by the way, folks. Right? Now. All right. And did y'all get why? Jay told you why. Y'all got why? Or the mass of water. And they're equivalent to each other. It's just a way of saying. Okay, I'm going to pause for a moment here because we got to reset up for the next part. Okay, so all right. I forgot to turn on the recorder again, but teams have done their measurements. They put the ice in and all that kind of stuff. Then they jumped to number 4, which should be number 3, conduction. Found the metal and plastic object on the bench since they've been exposed to the room temperature for quite a while. What temperature would you estimate that to be? And since the room temperature right here with them was, okay, change that to 23 degrees. That must have been warm up top. 23 degrees, each of them. But which felt warmer?
Plastic.
Okay, why?
And it has a higher conductivity.
Which did?
The plastic.
Really?
No, metal did not have. There you go.
Okay, the metal, the aluminum, conducted heat away from your face, which made it feel cooler, room temperature, whereas the plastic had a very low conductivity, meaning it came pretty rapidly to close to your face temperature. So, what you were sensing was room temperature with the metal and your face temperature with the plastic, or something pretty close to it. Make sense? Okay, now all of you check and see if your ice melted. And if it did, take the temperature, did it? Take the temperature of the iced water. Did yours melt? Okay, you got the temperature of the iced water? All right. Now we're ready to go back up to Roman numeral 2E. Okay? Now I don't know if I need to write this or not, but y'all probably know it yourselves. We have just had some leakage in here. Yeah. Okay. Okay. Now, number E. Okay, we're back on the last experiment, the one that you did with the cups. Okay? write the equation to determine the heat loss of the original water and then determine the heat loss. So what equation do you use? What happened to that original water? It was at a mass of whatever you had and a temperature of whatever you had. What happened to the water? It got cooler, so you had a heat loss. What is the equation that describes that heat loss? Q something equals something, something, something. Okay.
That was M something delta L, wasn't it?
Q is equal to
MC delta T.
MC delta
Capital T.
T, change of temperature. That's your equation for number E, the first part of E, right? Agreed?
Yes.
Okay. Now, we need to determine that. Now, each team is going to have different answers, so don't be thinking somebody else calls out an answer, you to put it in. What was the mass of the first water, the original water? You record that and put it right here. Okay? So many grams. This is 2A, the mass of that water. Right? Now, what was the C for the water?
It's just one, isn't it?
Yes, that would be 1 what? 1.00 what?
Calorie.
Calories
Gram
per gram
degrees Celsius.
degrees Celsius. Okay? Now, the next thing is what was the change of temperature of that original water? It started off being whatever your temperature was, and it ended up the temperature of the iced water. So what's the change of temperature there? Well, you do it yourselves. I mean, it's going to be different for each group, probably. Probably pretty close, but no, not all that close. You had different amounts of ice. In other words, the temperature of B minus the temperature of D. That's your change of temperature. You got it? So here's the middle part. You use the mass you got from A and the difference in temperature from B minus D. Say again?
B&D of 1 or B&D of 2? Because there's multiple B&D. Do you mean B of D?
No. Two.
Okay.
Yeah. We're doing Roman numeral 2.
He just gave us C. He gave us C.
Okay.
Is that what we're supposed to do?
This equation should have been calculated. Yeah, I got it. Right. And then multiply. Yeah, I got it. Okay. All you do, this is grams, this is calories per gram degrees Celsius, and that's degrees Celsius. What is that? 27. So you have from 45 to 18. And that should be calories. Okay? So you should have gotten a pretty good sized number. I'm guessing between, I see a 5,000 and 8,000, 5,000. Oh, good. Okay.
That's so you have to put 8.
You almost had some pretty
We put
good
calories.
quantity of rice. Yeah, you have a lot of rice.
We put total calories.
No, calories. Oh, no, just leave it in calories, just for now. Thank you. Okay. Now, we're doing F. Now, write the equation to determine the heat gained from the melting ice. The ice started, now here's your assumption, The heat gain, no, heat gain from the melting ice. So what formula would you use to,
Is it Q over MC?
okay, say that again?
Q over MC equals delta time?
Okay, no. The heat, it's still a heat, right? The equation determines the heat, that's still Q, gained by melting ice. So I'm going to put M here for melting. How much ice did you have? All right, what's the formula first? Anyone that make a guess?
Mass.
Mass, good, guess.
C.
It's like that L thing, right?
The L thing, which L thing?
Fusion.
Fusion, L sub L. Okay? The mass, this is the mass of your ice. This is the mass of the original water. This is the mass of the ice. Okay? So whatever that mass was, what is your latent heat of fusion for what? For ice to water? Anyone remember? It's in
It's
your book.
0.5, isn't it?
No, way bigger. The latent heat of fusion for water to ice, ice to water.
No, you said 0.5, so I said no.
Way bigger than 5.
One, it's
Way bigger than what? That's the specific heat of water.
Water, 80 calories
80. 80.0 calories
per gram.
per gram. And this was in grams, right? Your mass of ice in grams. The grams will cancel out. That will give you calories. So there's the formula right here. You do the calculation.
So are we doing the mass of just the ice?
Just the ice. That's all that melted was the ice.
So these times mass.
So your mass of the ice times 80.
Add 24.
Mass of ice was number C, or letter C, top of the page.
305, right?
no, that's the ice.
That's the ice. Okay, thank you. Yes, keep it.
80.
Okay, you do it yet?
Yes.
4,000.
Okay, what you get?
3,650 calories.
Okay, that seems reasonable. Got it yet?
Yes, sir. 30.
Sorry, I forgot.
Okay, 30. That sounds reasonable. What you get?
4,000.
Yeah, you don't have a lot of life. Okay? That was the heat gain by melting the ice. Didn't change the temperature, there's no delta T here, just melted the ice. So now, visualize this. You have hot water that cooled some, you have ice that melted, but we're going to assume on G that the ice started at 0 degrees, so there was no warming of the ice. So when it melted, it was still at 0 degrees. Okay, so G says, write the equation to determine the heat gained by the melted ice water. Not all the water, just the melted ice water, and calculate the heat gain. So what formula would you use? One of these two or a different one?
The second one.
No, it's already melted. This is only for changing phase. Once you melted the ice, it's now water, and it's going to warm up, have a change of temperature. So you go back to this one, but the difference here is your Q. Now this is Q for warming the ice. This was cooling the water. Warming the ice is actually ice water, okay? What is the formula?
MC delta T.
M, and this is M of the ice though, not the water. C delta T. Okay? This is delta T of warming. This is delta T of cooling. So the mass of the ice, each team has a mass. What C do you use? 1.00 because it melted, it became water. So it's 1.00 calories per gram degree Celsius. Right? Now, what was your delta T as you warmed that ice water? It started at 0 degrees. Where did it end up?
30.
Somewhere. That was number D, right?
Yes.
Okay, so it's D minus 0, which is D. Okay, whatever your D was, that's what you put here. Okay. And then you multiply those together, and that's degrees Celsius. Multiply those together and see what you get as your heat gain from warming.
Okay. Yeah, trust me, pretty blind. I think we've noticed that. And all of this.
Okay, you got something yet?
I'm still like that.
All right, that sounds reasonable.
We got roasted. It's like a big bag. I think it's like a honeycomb. Yeah, 1,000.
Oh, that sounds reasonable. What you get? That sounds reasonable. That sounds reasonable. Okay. Now number 8. H. Letter H. You add the two heat gains. That was F and G. Those are heat gains. Not the heat loss, the heat gain. Add those two heat gains and see what you get. Add F and G number and see what you get.
Again, you guys gotta keep an eye on these.
All right, good.
Wow, big rain. Mega mind is shaking.
I want to see your calculation on that. Your mass, there was 305. Okay, let's go to 305. Okay. Now, the temperature loss was 27 degrees. 27. Yeah, I know it. Then this is 7 times 80. Right? This was 18 times.
Like I'm almost certain they cut them off, so now they do it.
I don't know. I'm guessing right now you had so much ice you didn't run all of it melt. I don't know.
I think it did melt because I like stirred it around for a second to be sure too.
Okay.
Just so I can get it.
All right. How'd y'all do?
510 calories.
Okay. Oh, there it is. Okay, that's pretty good. Okay. All right. Now, you see your total heat gain. What you do now is compare the heat loss, that was E's answer, with the total heat gain, that's H answer. First, figure out what the difference between those two is. The difference between the answer for E and the answer for H. Heat loss and heat gain. Do a subtraction, see what you get. Okay.
I don't think, like, because it was just being E subtracting by H.
That's minus that.
I did it right. I can read sometimes.
That's what, that's it. Calories.
And the larger is the loss.
Pretty good. All right. Now, the next question says, which was larger, the heat loss or the heat gain?
The heat loss.
It may be different for different groups, so you tell what it was. Yours was heat loss? What was yours? Loss. What was yours? Loss. What was yours? Gain. Now, the question, okay, this is not something you have to write down, but I want you to do it anyway. That difference that you wrote down, take that number, okay, and divide it by the larger between heat loss and heat gain, E and G. No, I'm sorry, E and H. Whichever is larger of those. Take your difference and divide it by the larger of those two. What?
8.1. We're doing it in percent.
Yeah.
It'd be 9%.
Good deal. That's a good one. Take this 584. Okay, this you don't write it down here. 584 divided by which one of these is good? 60, number 60. Good deal. 32%. Pretty high. But it's okay. Don't write it down anywhere. I'm just wondering. How did y'all do? Okay. Good deal. Okay. That was just to let you know how good you are. I don't know what went wrong on yours. I think you had to have used.
We had a lot of ice.
Yeah, I know, but what was your mass of water?
Mass of water? Yeah.
Say again?
305.
Say again?
305.
What was your mass of water?
339.
Okay. I don't.
I mean, you checked our math. So.
Yeah, I did.
Yeah.
Okay.
Through our mass of water is 362.
Okay.
I think we just
That's
had
all right.
so much ice.
Okay. Now, the question is, why was the difference there? And partly, why was it? Those who are less than 15%, you're not really concerned with that, but it was, one of them was higher or lower. Okay. Now, yours was which was higher?
Heat loss.
Heat loss. What was your final temperature? 30 degrees. Okay. I would say yours is probably just experimental error because the temperature in the room was awfully close to that. So that's just experimental error. Anything less than 15% would be okay that way. What was yours?
Ours was 8.8%.
Okay, yeah. But
30 degrees of ice.
yours was heat loss?
Yeah, heat
Okay.
loss.
And what was your final temperature? 30 also? Y'all got the same thing, okay? Probably just experimental error. I think anything within that is good. Yours was, okay, yeah, but I'm more interested in
I know that was from Milton
26, okay? That's below, so you picked up a little bit of heat from the room. Not much, because that's pretty close to what room temperature was, but you picked up a little bit, okay? So that's probably why yours was, but experimental error would work too. Let's see what yours was.
That was like 32%.
Okay, and heat loss. And here's, okay, heat loss. Yeah. Because this was so much colder than room temperature, all the time you had it uncovered, it was losing heat. Yep. Yeah. Yeah.
I'm thinking wing.
Your temperature is
I think we just had so much ice, so we just got really cold.
yeah,
And then we
but
got it later, so maybe we got it like perfect time where it was just like melted. So we just cold.
yeah, but it still should be a bit closer to that. I just can't see why.
Yeah. Dad was checking my math too, just in case. So it wasn't just missing.
It probably had to do with that, but it should have balanced out. So anyway, yeah. All right. Any questions on these?
You never said why.
Huh?
Why?
Oh well, yours was experimental error because you're within range, and you're in this group. Let me just see. Okay.
got all the new life.
What was the, is that the they are pass?
She lost. Don't do college. No.
I got some rice.
You know what? Right.
That's good. All right. Thank you. Any questions on the lab? Your deal, folks? I hope I didn't put you out of too many of your tuition dollars, okay? Good deal, thank you. All right, see you tomorrow.
No, not tomorrow.
Good deal, thanks. Okay, what we'll be doing Thursday, I think, okay, we'll finish chapter 4, start on chapter 5. We'll get far enough on 5, and we'll do the first lab for chapter, not 5, 6. We'll do the first lab for 6. Okay, so you'll need to either get one of these guys to either get the data for you, or you can get a lab for you, fill in the data, and then figure out,
So
listen to the,
Tuesday we'll be having this.
yeah, on chapter 4. Yeah, the one that we almost finished today. And we may have the lab, the second lab on 6.
I'll be good for those days.
Okay.
As long as they're, make sure if I need to study.
I gotta go back home.
Yeah, well, you make it up.
I gotta get my stuff put out.
Some of that. And listen to the video.
Oh,
Okay.
so you trying to take it on the fifth?
Yeah, that one. I was trying to.
End this.